Hi everyone. Today let's talk about section 1.5, quantifiers. Propositional calculus versus predicate calculus. What we have been studying in the last two sessions is propositional calculus, the study of statements which are specifically either true or false and the logical connectives and or implies and the not operator. So those are the propositional calculus. A predicate, which is also called a propositional function, is a more complex situation, but it is related. Okay, here is the definition. Let P of X be a statement with variable X and let D be a set. We call P a propositional function or predicate if for each X in the set D, P of X is a proposition. So P of X is either true or false. We call D the domain of the discourse of P. Okay, the domain of the discourse specifies the allowable values for X. Do you remember before we talk about propositions? So X minus 3 equals 11. This is not a proposition. Do you remember that in session 1.2? Okay. And actually, this guy is not a proposition, but it is a propositional function. Okay, so it is a predicate propositional function. Okay, we can let the domain of discourse be the real numbers. Okay, then for X in the domain so D P of X is a proposition. Okay, so for example, we can pick 14. 14 is a real number. So P of 14. So 14 minus 3 equals 11 is a proposition. And it is true, right? If it's a proposition, we can tell whether it's true or false. However, 13 minus 3 is 10. It's not 11. So then P of 13 is false. Okay, so this is a propositional function. It's not a proposition, but when we plug in specific values in it, we get a proposition, and then we can tell whether it's true or false. Okay, so let's look at the example. Let P of N be the propositional function predicate. N is an odd integer, where the domain of discourse is Z, the positive integers. Is P of 3 true or false? So what does P of 3 means? So we plug in N equals 3, right? So we get 3 is an odd integer. Okay, so 3 is an odd integer. Is this true or false? Well, this is true, right? And then is P of 6 true or false? So 6, we plug N equals 6 in it. So 6 is an odd integer. Is this true or false? Well, 6 is an even integer, right? So 6 is 2 times 3. Okay, so it's an even integer, then this is false. So far, so good, everybody? Okay, let's continue to look at more examples. Examples are the following propositional functions. Okay, let's see. First one, n squared plus 2n is an odd integer, where the domain is positive integers. Well, that is true, right? Because this guy is P of n. And the domain is positive integers. So that is the D. Okay, next. X squared minus 3x minus 2, where the domain are, and this is a propositional function, right? And P of X is this quadratic equation, and the D is the R. All right, so far so good, everybody. Okay. So we should say, okay, yes, it's a propositional function. Yes, it's a propositional function. Next, the person is greater than 5 feet 10 inch, where the domain is the set of people from Sweden. Okay, this is a propositional function. Yes, because we don't know what the person is. Okay, so we don't know what this person. So the person is greater than 5 feet 10 inch. I think there's a typo. There's no error right there. Okay, so this is P of the person. I don't want to use P for the person. Okay, let's call the person is X again. So this is P of X. And yes, this is a propositional function, and the domain is the set of people from Sweden. So this is the D. Okay. However, I'm gonna make, if I change this sentence a little bit, oops, let me change the color here. Okay, so if I change this sentence, if we replace the person by, let's say, Jack, okay, then we get Jack is greater than 5 feet 10 inch. Well, this is a proposition, then it's not a propositional function. Okay, because we know that the person is Jack. Then in this case, no, it's a proposition, not a propositional function. Okay, as a function, we need to have a variable. Okay, let's continue. Next, 1 plus 12 equals 6. Can we say this is true or false? Yeah, we can say it right away. So this is not, this is not a propositional function. It is a proposition. So no. Okay. So far so good, everybody. Okay, next. There exists x such that x is less than y given a y value. So x and y are real numbers. Okay, now let's see. Okay, so how do we say that? Okay, so P of x is x less than y. Okay, and the domain is real numbers. Okay, so is this true? Okay, let's see here. Do you see there exists x? So we don't know what x is, but here it says there exists x such that x less than y given a y value. X, y are real numbers. And actually, this is a proposition. It's a propositional function. Okay? And this is a propositional function with existential quantifier. Existential quantifier. And we will talk about what is existential quantifier. So there exists the notation for it. So there is there exists x such that p of x is x less than y given a y value. And, well, this is true because because we can let x be y minus 1, then x is always less than y. Okay, and we can do that because we just need to pick a real number, which works. Okay, we will talk about more today, existential quantifier and the universal quantifier. Okay, next. What is universal quantifier? We often use quantifier, also called universal quantifiers, for a given propositional function. So given the propositional function p of x, well, that is x squared greater or equal 0, okay? Where the domain is R, consider the statement for every x, p of x. Well, this statement is now either true or false. Okay, we write this proposition in shorthand for all x. So this symbol means for all. Okay, so for all x, p of x. So then p of x is universal quantified. The statement is now specifically true or false. It is a proposition. So, how do we show it's true? Okay, so if this p of x is satisfied for all the x in the domain, then this statement is true. If there is one x such that the p of x is not satisfied, then the statement is false. Okay? So, the other words, for every, for all, for any, they are all universal quantifiers. You can use the symbol for all. Okay, this is a symbol for all. It's like the letter A and then it's upside down. Okay. Alright, caution. For a different x, p of x is a different proposition. Okay, and for all x, p of x, this statement is a proposition. It means that for all x in the domain, p of x is satisfied. Okay, p of x is true. To find a universally quantified statement false, you just need to find one counterexample. Okay, we just need to find one value that p of x is not satisfied, then the universal quantifier is false because it's not true for all x in the domain, right? And then to show that it is true, well, then you have to show no matter what value you pick from the domain, this p of x works. Okay? Yes. We need to let x be arbitrary in this case. So far, so good, everybody? So we will do some examples here to help us to understand. Okay, let's see here. Is the statement for all x squared minus 1 greater or equal to 0 true or false if the domain is R? Okay, let's think about it. X squared minus 1. So x squared. Well, think about x squared. What is x squared? Well, this is a parabola, right? X squared is like a parabola like this. And what is the smallest values can it be? Oh, I would say the smallest value is 0, right? So when x is 0, x squared is 0. Okay, let's try to plug in. When x is 0, we get x squared is 0. Then x squared minus 1 is negative 1. Wow, is this guy greater or equal to 0? No, this guy is not greater or equal to 0. So see, we have find a counterexample. So there is an x value such that the p of x is false. Okay, so that's why this gives us a counterexample. So the statement is false. Okay, everybody? Yes, because the statement for all x, this guy happened, as long as we find one value such that this does not work, then we can show it's false. Okay, next. Is the statement for all x squared minus 1 greater or equal to 0 true or false if the domain is z plus positive integers? So positive integers is like 1, 2, 3, etc. So in this case, well, x guy, so x is greater or equal to 1. Well then, look at our picture. 1 is here. When x is greater or equal to 1, what happened? When x is greater or equal to 1, we're at this piece. X squared minus 1 is actually greater or equal to 0. Oh, maybe we should put x squared is greater or equal to 1. So x squared minus 1 is greater or equal to 0. And this is for all x, okay? This is for all x. For all x in the domain positive integers. Okay, that's why now we have shown this statement holds for all x in positive integers, so it is true. Okay, next. It's the statement for all x squared greater than 0 true or false if the domain is R. Well, this is false, right? Because we just said if x is 0, then x squared is 0. It's not greater than 0. So this gives us a counter example. So then that's why this guy is false. However, how can we make this statement true? So we mark here how do we modify the domain to make this statement true? Okay, so how to make this statement true? Okay, so change the domain to be R positive or R negative. Actually, as long as it's not 0, okay, as long as you delete the 0 in it, then this statement is true. Okay, no matter x is positive or x is negative, x squared is always positive. So far, so good, everybody. So remember this guy is set minus. Set minus means it's the real number line, and then you take out the point 0. Okay, so we put an open circle at the point 0. So far, so good, everybody. Okay. Next, let's summarize here. Again, to prove a universally quantified false is easy. You just find one value from the domain, which makes the universally quantified statement false. Generally speaking, to prove a universal quantified statement true, you have to prove it is true for all values in the domain. You either test all values of the domain or it involves writing a proof. Okay? You cannot prove a universal quantified statement true by showing that it works for one or some elements of the domain. You must show it works for all the elements in the domain. Okay, so just be careful, cannot. Okay. Let's look at this statement. Is this statement for all x, 1 over 1 plus x squared less than or equal to 1, true or false if the domain is R? Okay, let's see. What do we know? Okay, we know, okay, let's see. X in R, right? Then x squared. What is x squared? We know x squared is greater or equal to 0. right? Then, okay, this is what we know. How do we get from x squared to this guy? Well, you see x squared is in the denominator. But the denominator is not only just x squared. We have x squared plus 1. So, what do we do here? So, x squared greater or equal to 0, then you can add 1 on both sides. Adding a number won't flip the inequality. So you have x squared plus 1 is greater or equal to 1. And then you're gonna flip it over. Okay, 1 over 1 here, 1 over x squared plus 1. When you flip it over, it actually changed the inequality. Why is that? Think about it. 3 is greater than 2, right? When you flip it over, 1/3 and 1/2, which one is bigger? Of course, 1/2 is bigger, right? So when you flipped both sides over, it actually flipped the inequality. So 1 over 1 is still 1. Oh, see, we have shown that 1 over x squared plus 1 is less than or equal to 1. And it is true for all x in the domain real numbers. So that's why we see this is true. And this is a proof. Okay? Alright. We can say let x be in R, and then x squared greater or equal to 0. We add 1 on both sides, and then we flip it over, and then we get 1 over x squared plus 1 less than or equal to 1. Okay, so that is for the universal quantifier. Next topic, existential quantifier. So consider the statement there exists x such that x plus 2 equals 3 in the domain z plus, that's the positive integers. Okay, the shorthand there exists. Well, this is like the E, but left and right we flip it. So yeah, it's kind of funny. For all, universal quantifier is like the A upside down. Existential quantifier that exists is like the E left and right we flip it over. Okay. So there exists x plus 2 equals 3. We say the propositional function p of x is x plus 2 equals 3 is existential quantified. The statement is now true. It is either true or false. So it is a proposition. There are existential quantifiers. So this is other words we can represent it. And you can use the symbol, this symbol, there exists. Okay, to prove a propositional function with an existential quantifier true, you only need to find one value in the domain that make the propositional function true. And now to prove an existential quantifier false, you must show that the propositional function is false for all values of the domain. So far, so good, everybody? Okay, a lot of definition, right? Let's look at the examples. Examples help us to understand. Example is there is x squared minus 2x minus 3 equals 0, true or false, if the domain of the is R. Well, this is quadratic function. Do you remember quadratic function? Okay, so quadratic function is parabola. Parabola, there are 3 cases. Okay, so here we have 2 real roots. And we can have 1 real root. And we can have no real root. Well, if we have no real roots, it means we have 2 complex roots. Okay, So 2 real roots. When do we have 2 real roots? Okay, suppose ax squared plus bx plus c equals 0. And then what is the quadratic formula? Well, that is 2a negative b plus or minus b squared minus 4ac, right? When do we have 2 real roots? Is when the things inside the square root is positive. So we call this guy discriminant. B squared minus 4ac is positive. And when do we have 1 real root? Is when the things inside the square root is exactly 0. So the discriminant is 0. When do we have no real root? Well, that's when the discriminant is negative, because square root of minus 1 is defined to be I. So you're going to expect to have like alpha plus or minus beta I. You're going to have complex conjugate roots. Okay, now let's see. Here, so in order to see whether we have a root, we can either factor it or we can find the discriminant. Let's try to factor it first. Maybe we can factor it. Okay, can we factor it? So x, wow, yeah, negative 3 and plus 1 will do the job, right? Negative 3 plus 1 will give us negative 2. So this means x is 3 and x is minus 1. Yes, this is true because the domain of disclosure is R. So we can find the two number 3 or minus 1 such that this proposition is true. Okay, so this is true. Their excess means if we can find some value satisfy this propositional function, then this is true. Okay, next, can we factor it? I don't think so. 5 and 1 won't give us 2. So let's check the discriminants. It's b squared, so minus 1. B is minus 2. Okay, so minus 2 squared minus 4. A is 1, C is 5. 2 squared is 4. 4 minus 4 times 5, 20. Negative 16. Oh, you can see it's negative, so no real roots. There's no x such that this could happen. So that's why it's false. Okay, so no, because no real roots can satisfy this quadratic equation. So far, so good, everybody. See, for existential multiplier statements, to show it's true, we just need to find value to satisfy the propositional function. And to show it is false, we must show that there's no value can make this work. Okay, let's continue. There exists a prime number n such that n plus 1, n plus 2, n plus 3, n plus 4 are not prime. The domain of is z plus. Okay, let's see. There exists, if we want to, usually how to say whether it's true or false, we plug in some number. We first plug in some number to see whether we can find some value works. Well, if we plug in so many numbers and it's still we cannot find it work, then maybe it is false. Then we try to show it is false for all the values. Okay, so first of all, what are the prime numbers? Okay, let's go through the list and see whether it works. The prime numbers are 2, 3, 5, 7, right? But 7 won't work because, okay, 7, let's see, 7, and then we have 8, 9. So n plus 1 is like 8, n plus 2 is like 9, n plus 3 is like 10, and then n plus 4 is 11. 11 is prime, so 7 doesn't work. Okay, next, 11, we think about, okay, 12, 13, oops. 13 is there, so 11 doesn't work. How about 13? 13, then we have 14, 15, 16, 17. Well, 17 is prime, so it does not work. Let's go down the list. Okay, 17, so 18, 19, oops, 19 is a prime. So, okay, now let's see here. 19, okay, 20, 21, 22, 23. Oops, 23 is there. So, okay, let's see, 23. 23, we have 24, 25, 26, 27. Oh, it works. None of them are primes. So now we have find the prime 23, and then the next 4 following numbers, they are not prime. Now we have found this number. So there exists, yes, there exists that number is 23. It is prime, but the next 4 following numbers are not prime. So this is true. Yeah, sometimes you really need to go down the list until you find one word. Or if you go down so many, you realize you cannot find one, maybe you can try to prove it is false. Okay, it doesn't work for all the numbers. Alright, next. Is the statement there is x, such as 1 over 1 plus x squared greater than 1, true or false? If the domain is R. We saw this last time, right? Okay, let's see. We start with, because domain is R, okay? Let's see. Let's randomly just pick a number. Okay, let's check. If we pick x is 0, what do we get? We get 1 over 1 plus 0. It is 1. Well, 1 is not greater than 1, so 0 does not work. Okay. Let's pick 1. If x is 1, then 1 over 1 plus 1 is greater than 1. No, 1/2 is not greater than 1. See, we find 2 values and it does not work. So maybe this statement is false. We cannot find such a number. But however, to show an extension statement is false, you cannot just pick 2 values. You have to show the proposition is false for all numbers in the domain. Okay, so you got to prove it here. So let's see. This is a proof. Let x in R be arbitrary. Arbitrary means it's any number, and let x be any real numbers. Okay? And then, well, what's x squared? Well, x squared is greater or equal to 0. This is what we know, okay? And then, how do we get from x squared to this expression? Well, look at the denominator. We add 1, right? So x squared plus 1 is greater or equal to 1. And then we flip both sides. So when we flip both sides, it's similar to what we did before, right? When we flip it over, it's gonna flip the inequality. And see, now we have shown that for all x in R, 1 over x squared plus 1 less than equal, so not greater than 1. So now we have shown all values in the domain. The propositional function is false. So that's why it's false. Okay, so far so good. No x in R can satisfy that proposition. So that's why this existential statement is false. Okay. Alright, so let's take a little break here. Okay, we'll continue in video part B. Okay, see you soon.